What's up, algebra? Ooh, no, AP Calculus. Wow, I'm off my rocker today. This is a homework guide for 4.4.2. We're going to be doing problems 146 all the way through the end of this assignment, which is problems 154. All of them. They're all good. They're all pretty straightforward. Let's see how far we get before we run into any mistakes or problems along the way. So here we go. 146. We're going to start by evaluating a bunch of integrals. First of all, we're going to throw away problem A, because right now there is no way to do this. We do not have an ability to evaluate that integral yet. We will later on in this class, but right now we don't. I'm not particularly a fan of the way they throw these problems into homework assignments, I'll be honest with you. I wish they would just leave them off until we have the tools for you, but I suppose it is cool to see what you will be able to do later on if you're that kind of person. Question B, though, is totally doable. It's an indefinite integral. There's no numbers there. So what we're going to do is we're just going to find the antiderivative and put plus c on there. Might be helpful to write that the original function, the f, lowercase f of x in this case, is 4m to the negative third minus 3 cosine of m. I guess if I'm being entirely clear here, that's f of m, not f of x, since m is the variable. Now we're looking for the antiderivative, capital F of m. So we're going to have to go back in time a little bit. Let's take the degree of m up to negative 2, and then consider that negative 2 times whatever's in front has to be 4, so negative 2 must be there also. As far as the cosine goes, that's actually really easy. It's just going to be minus 3 sine of m, since the derivative of the sine will give you the cosine, and the 3 is a constant multiplier, and the derivative is not affected by it. Let's just remember to put plus c out there for the full points, and that's all you're looking for. For question C, this is a really interesting antiderivative to calculate, but we will never have the ability to do that in any sort of calculus. However, we do have a calculator here for us. That is the best way to evaluate this. So alpha f2, option 4, we're looking for the integral from 1 to 2 of x to the x power, which is an interesting function outside of the scope of this class, but we can at least have the calculator crunch that number for us. It's going to be about 2.05, which is pretty good. As far as question D goes, question D is also incredibly easy if you realize what's going on there. Pi squared is just a constant. It's always going to be the same number. There's no x involved in its expression at all. So this is just going to be the antiderivative of that, which is really easy to express. It's just x times pi squared plus c. And there you go. If you were to take the derivative of that with respect to x, the pi squared would stay and the x would go away, and your plus c would go away also, and you'd be right back where you are. Pretty simple. And then question E, you could do this on a calculator, but you don't need to. Absolute values and linear expressions inside of an integral, this is a good place for you to use just geometry to find the area under the curve from 0 to 5. Because the only shapes you're going to see here are going to be like triangles or maybe a trapezoid at best. Let's actually take a minute to try to doodle this picture here really quick. This is question E. We're looking for the integral from x minus 2 plus 3, integral from 0 to 5, of the absolute value of x minus 2 plus 3 dx. If we graph that function, this is an absolute value that's been moved to the right 2 and up 3 spaces. So if we try to doodle a little graph of this thing from 0 to 5, it's got a vertex you might think of at 2, 3. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So it's got a vertex at 2, 3, and then it's only got a slope of 1 going in either direction. So if we're going over to 5, it's going to look like this. Kind of. I'm trying to draw at least a little bit accurately. I guess I didn't really think about my scale very clearly there either, did I? So we're really just looking for this area under that curve. So I think the best way to do this is to think about it as 2 trapezoids. Cut it into boxes that way. This is going to be 2, this is 3. If I were to plug in 0, it would be 2 plus 3, this is 5. If I were to plug in 5 for x, 5 minus 2 is 3, 3 plus 3 is 6, and this is 3 down here. So this is just going to be a couple of trapezoids. The first one is 1/2 times 5 plus 3 times 6. The second one is 1/2 times 3 plus 6 times 3. So the first one 8 times 6 is 48. 48 divided by 2 is 24. That's what this area is there. That seems really large, but I'm going to go with it. Is that what it is? Oh, times 2. What am I doing here? Sorry, I was like, that's way too big for that area. Sorry, okay. Okay. This is just 8 then, because the 1/2 and the 2 cancel out. I imagine you guys, when you watch these videos, are pretty frustrated with, like, what are you doing for it? And this is going to be 27 over 2. That is, just a second, brain rebooting, 13.5. Yeah, and it all adds up to 21.5, which is the answer I have on my answer sheet that I have on the other monitor, just to check to make sure I'm giving you the right answers. There you go. Okay, 21.5 is the answer to that. You could use a calculator for this, but you wouldn't need to. I guess that's the point of this problem. Next question, 4147. Draw a flag that will generate the same volume if it's rotated around the X or Y axis. And is there more than one possibility of shape or flag? Does your flag have any special property that ensures those equal volumes? Honestly, any one drawing you can do, you find it might be useful to sketch an X or a Y axis. This is 4147 off to the side here. The one that springs to mind for me is if you go any equal number of points up and to the right and then connect them like this, that area there, since it's 2, I guess in my example, it's 2 on both sides. So if you were to rotate it around the x-axis, and you get a cone, and if you rotate it around the y-axis, you'd get the same cone, since it's the same thing. There's nothing special about this area. You could do that same thing with any, like you could do 3 and 3, or 4 and 4, and 5 and 5. I think geometrically, if you want to talk geometry for a minute, if you were to draw this line here, which is the line y equals x, as long as the shape you come up with is symmetric to that line, you'll get the same thing when you rotate it vertically as if you rotate it horizontally. So, I mean, you could do all sorts of fun things. You could do like a curve like this, something like that. It's got to be symmetric though. And now if you rotate it vertically or horizontally, you're going to get the exact same thing. So there's a lot of different drawings you can make for this one. 148, without your calculator, evaluate the following limits. So we're on our own here. So, well, with this first one, with A, it's pretty obvious you can't just plug in 3. Or, no, you can. 3 minus 3 is 0. Square root of 0 is 0. So this is 0. What am I talking about? The rule with limits is if you can plug in the number, if you can plug in 3, plug in 3. Go for it. With B, you can't plug in infinity, unfortunately. But you don't need to, because the trick with this question is that the bottom is going to be much larger than the top, because the bottom is x to the third power, and the top is x to the second power. X to the third power, these all go to infinity. If you plug in infinity for all of 3 of the x's in this problem, they all go to infinity. But the bottom, x to the third power, goes to infinity faster. So you're going to get, basically, you're going to get a smaller infinity over a bigger infinity, which is always going to approach 0 over time. So it's also 0. And then question C, the limit as x approaches pi of this. Now, I don't like this problem, I'm going to be honest with you. The reason why, well, we could think about it like a derivative question. That's how I want to think about it. Yeah, no, I withdraw. I do like this question. It does require that you see the fundamental version of the derivative here, especially this one. The limit as x approaches c of f of x minus f of c over x minus c. That is the other version, the formal definition of derivative. If you see that version in here, this problem is actually really simple, because this would equal f prime of x is basically how the formal definition of derivative is. That lets you see pretty clearly that we're looking for the derivative of the cosine of x, specifically when x is equal to pi. So what we're looking for is, what is f prime of pi if the original function is cosine of x? This is a pretty common AP style question. It's actually really simple when you get the hang of it. So don't get discouraged with this one. This ends up being what is the negative sine of pi, which is also 0. Since sine of pi is 0, so the negative doesn't matter. All 3 are 0. Interesting. 149 asks us to use our calculator to approximate the following limits, accurate to 3 decimal places. 3 decimal places is the standard for the AP Calc test, so make sure you're following that rule as we go through this. All I would do in this problem, for this first one, let's bring up calculator cam. First thing I would do is I would just plug in 1, honestly. I don't think it's going to create 0 on the top or the bottom, or will it? It will. Yeah, because 2 to the first power is 2 and 3 to the first power is 3. Let's look at the graph. Let's go make a fraction, and we'll go 2 to the x minus 2 over 3 to the x minus 3. And then we'll just make a window, and I really only care about what's happening when x is 1, so I'm only going to change my x to -1 to 2, I guess. That'll put 1 kind of right in the middle. I guess 3 would be better. There, I'm just going to take a look and see if I can get this picture there. I'm interested in what's happening at 1. I'm hoping there is a limit that it does. Looks like there is. Looks like it is doing something crazy there. I'm not really sure what it is, but... Now, in this case, it might be better to look at the table. The table can probably give us a good view. So I'm going to go into table settings. I want to start the table at 1, where I believe there is an error, but I'm going to make the delta table, the change in the steps, I'm going to make it like 0.0001, something really small. That way, when we look at the table, we can see what's going on right around there. Yeah, see, look. See, the limit is clearly approaching 0.4206 from both sides. At 1, there's an error, but on both sides, you're getting the same thing. So this is about 0.4206. So my advice to you is use the table feature of your calculator. Use the table. That's the best one. Let's try B also, which I think is probably going to be the same kind of thing happening. Yeah, if we plug in 0, we're going to get the same problem. So we'll just program this into y1 and see what happens on the graph. 1 minus cosine of x over x squared. This is going to give us a 0 on both things. Let's go ahead and just consult the table right away. We're going to start our table at 0. And again, I'm going to make my delta table like 0.001, something very small. We'll look at the table there, see what's happening. It's 0.5, see? Right around on both sides is approaching 0.5. We could probably graph this and see that also, 0.5. Like that. This is a good idea. A limit can exist even if there's a hole in the graph. If we graph it really quick, yeah, it's almost a straight line. Look at that. We're kind of zoomed way in on this little chunk there, so it's not actually a straight line, but yeah, okay. Anyway, let's move on to the next question. Write the equation of the line that is tangent to the function that thing at x equals 1. So what we're going to need to do here is we're going to need to figure out what the derivative of this rational function is at x equals 1. Again, when we say we're going to write the equation of a line, we always want to be thinking right away about good old point-slope form, which in AP Calculus kind of has a new, fresh coat of paint, you might say. Instead of x1, we think about some given value a. In this case, that's going to be 1 right there. So we know that a is 1. What we need to know is what f of 1 is. So if I plug 1 into this function, let's see, we get 3 minus 12, which is -9, over 3, which is -3. So there's that. Now the last part we're going to need is the derivative. And what's unfortunate about this is that we don't have a tool for finding that derivative yet. But I think if we factor out that 3, we can get the x plus 2 to cancel out. Yeah, the original function, let's factor the 3 out. We would have x squared minus 4 over x plus 2. And this is equal to 3 times x plus 2 times x minus 2 over x plus 2. And so the x plus 2's can cancel out, and now we got something a little more beneficial. This is 3x minus 4. If we redistribute it. And that's actually pretty nice because the derivative of that, y prime, is just going to be a very constant 3. If we were to graph the original y function, this is a good example of a graph that looks like a straight line, but it's got a hole at -2. And so it looks like a straight line, and the straight line is going to have a constant slope of 3. So the derivative is always 3, no matter what, because derivative measures the slope of the original function. So f prime of 1 is 3, like that. And we can use this information now to build the equation of our line. It goes y minus -3, or y plus 3, equals the slope, which is 3, times x minus 1. And we will stop there. It's not necessary for us to go any further, If you wanted to, my answer sheet has the slope-intercept form, but it's unnecessary. If you subtract the 3 from both sides, you get 3x minus 6. College Board doesn't care. If they ask you for this on a free response question, stop right there. Don't go any further. Let's go to 151. Let's see. The annual cycle of daily high temperatures in Cabanaville is shown at the graph below from January to December 31st. X-axis is marked in months, and the y-axis represents temperature in degrees Fahrenheit. Approximately when is Cabanaville at its hottest, and how can you tell? Well, this is the degree of temperature, so all we're looking for here is, how can I tell? I'm looking for the maximum point. This is not a derivative graph. This is a position graph. So I'm looking for this point right there. And I would just kind of eyeball where that's happening, drag it down to there. It looks like the 7th month. 1, 2, 3, 4, 5, 6, 7. Yeah, July. So it's at its hottest in July. That's where the maximum is. The question B, though, is the calculus question. When is the temperature changing the fastest? What is the name for this type of point on the graph? What we're looking for is where's the steepest slope on this graph. I see 2 of them on this graph. Once is right about here, and that's where the slope of the tangent line is going to be as steep as possible. The other one is over here, where the slope is negative, but it's also very, very steep. When is the temperature changing the fastest? I'm going to say about April, which would be month 4, and then again at September. I'm guessing. I'm just eyeballing the number 9 on this graph. It doesn't really matter too much where those are. What I want you to see is that those are the points of inflection. And those are basically where the slope is the steepest. It's the biggest number. And it's also where the derivative of the slope, or the concavity, equals 0. So when you're looking for a maximum or a minimum, you want to think about derivatives equaling 0. That's what you're looking for there. So those are the points of inflection we're looking for. 152 is a challenging question that we're going to do together right now. This is kind of like I like this problem a lot. We're determining the value of A such that f is differentiable at x equals 1. We saw a problem just like this on the last assignment where we had to prove it was differentiable. What we're looking for now is what the constant needs to be. This is very similar to our continuity questions, where we want to take these two things and make them equal to each other and solve for A, except for that's not quite what we want to do here. What we need to do, that would be to test if it's continuous. If it's differentiable, we care about kind of the same thing as continuity, but we care about the slopes being the same thing. Not just the y values to be the same thing, but the slopes that they approach have to be the same also. So we're going to do the same thing we do with continuity problems, but first we're going to take the derivative. F prime of x, which in this case would be 2 times x plus 2 for when x is less than 1. And it would be a times the cosine of x minus 1 for when x is greater than or equal to 1. So what we're going to do now that we've taken the derivative, we're going to do the same thing we do with continuity. We're going to make these two things equal each other. We're going to make x equal to 1, and we're going to solve it for a, essentially what we're going to do. It's actually really simple to do once you've realized that. We're going to check to see when 2 times x plus 2 is equal to a times the cosine of x minus 1. And we're going to plug in 1 for the x's in this problem, and then solve that for a, because that's what we care about. We care about when x is 1. So let me zoom in on that really carefully, and away we go. 1 plus 2 is 3, and 2 times 3 is 6. The cosine of 1 minus 1 is the cosine of 0, and the cosine of 0 is 1. And so that's it. That's the answer. A is 6. That's the answer. Pretty cool. That question's not actually that complicated, but it's a big jump mentally on like what to do if you're asked that question. You probably will be asked that question too. That's a probably, not a certainly, but a probably. The exact same idea as continuity, only you got to take the derivative first because you care about the slopes. 153, the graph of f prime is shown at right. Determine the intervals on which f is increasing, decreasing, concave up, and concave down. So we're going to do this problem right underneath this graph. I think it's a good idea to draw a little thing. So the first thing we care about is increasing or decreasing. So let's think about f of x. I'm going to put f of x here. I'm going to draw a number line parallel to the x-axis right there. Increasing and decreasing has to happen. Let's make a little chart over here because this is worth reviewing. Increasing means that f prime of x is positive, and decreasing means that f prime of x is negative. Since this is a graph of f prime of x, basically if this graph is above the x-axis, we're increasing. If it's below the x-axis, we're decreasing. So I see the zeros happening at -3 and at 2 and at 4. And it's very useful to do this right under the graph so you can kind of map it out from left to right. So we've got negative here, positive on this range, negative again on this domain, and positive on this domain. So the translation for us is that f of x is decreasing from -infinity to -3, increasing from -3 to 2, decreasing from 2 to 4, and increasing again from 4 to infinity. So we can answer that question right now. Let's write those findings down. So f of x is increasing on the intervals from increasing is what I wanted to do, on -3 to 2 and 4 to infinity. And it's useful, if this is a free response question, it would be useful to write this sentence because f prime of x is greater than 0 on those intervals. And then we're going to write the same kind of sentence. I'll switch colors. F of x is decreasing on -infinity to -3, and then again from 2 to 4. Again, because f prime of x is less than 0 on those intervals. Pretty cool. As far as concavity, we're going to do very much the same thing. I know I'm taking a little extra time for this problem, but I want to be really clear. For f double prime of x, now we got to think about how this derivative is changing. So f prime of x, or f double prime, is the derivative of this graph. So now we're going to look at our f prime graph and tell where is it increasing and where is it decreasing, because that'll tell us when our second derivative is positive or negative. So this graph increases up until this point. I'm going to mark it as approximately 1. I'm going to say it's 1. It's probably something else, but I'm going to call, -1, sorry. It looks like it decreases until this point, which is happening at 3. And so it's increasing, or positive, from -infinity to -1, decreasing from -1 to 3, and then positive again from 3 to infinity. And so the translation for us, when second derivative, we're going to have concave up, concave down, and then concave up again, like that. So again, we can write a couple sentences like this. F of x is concave up on -infinity to -1, square bracket, and 3 to infinity. And again, it's useful. If this is a free response question, your reader will be looking for this phrase because f prime of x is increasing on those intervals. Alternatively, you could say f double prime of x is greater than 0. Either way, you're signaling to your exam reader that you understand what it takes for concavity to happen. The same thing would be said about, let's see, which color haven't I used yet? Blue. F of x is concave down on the intervals from only one interval, from -1 to 3. And again, you could write either of those two phrases because f prime of x is decreasing on that interval. Oh, I'm writing over my face. Whoops. And again, alternatively, you could say because f double prime of x is less than 0. Those would be ways to signal to your exam reader that you understand how concavity works. This is a pretty straightforward problem, but we took a lot of time for it because I wanted to really demonstrate proper writing on this one. So there is the full description. It's a really simple thing to look at and go, oh, and figure it out. But it takes a little bit of time to express what's going on. The last question we're going to look at is kind of a bonus question. I'm not super worried about this one. This is not how it would show up on your AP test, but I'm just going to go ahead and walk you through how you can get the answer to this one. This is asking you to take this limit statement and write an integral, essentially. So first thing I noticed right away is we have 2 over n out in front here. That's going to be kind of the b minus a over n part, or the width of each one of these rectangles that we're adding all together. And so what you know is that your integral that we're eventually going to write, whatever numbers go on a and b, they have to be 2 spaces apart because it's a 2 right there. As far as the rest of it goes, we kind of have the same expression over and over again. It's 1 plus 2 over n squared, 1 plus 2 over n squared, 1 plus, and what you see here, here's the real key is this little phrase right there. Basically what you're seeing is this is 2 over n. That right there is 2 over n times 2. And so this is going to be 2 over n times n. That's what's happening there. 2 over n, of course, is the delta x that's going on there. So what I want you to see in each one of these little phrases right there, you're looking for kind of, hey, what's f of a plus your delta x I thing? In this case, I is n, but it's the same thing. We already know that delta x is 2 over n. So this is how I'm kind of going to say that a is equal to 1, which means the upper bound of the integral is going to be 3. And as far as what the function is, it's just something being squared. And so it's just x squared. And that's exactly what this is. This is x squared dx. If you were to break this down into and put it back into a sigma, it would be the limit as n approaches infinity of the sigma from I equals 1 to n. You would have your 2 over n in front for your width, and then you would have f of your it would be f of your left endpoint plus 2 over n times I. And if you substitute that in, that's going to be 2 over n, which you see out in front there, and then your f of x is going to be 1 plus 2 over n I, or n in this case, squared, since the function is just x squared, like that. That's a little bulky, but the more we do these problems, I hope you see that the integral notation is just so much better and so much more descriptive of what we've been doing. But it's important to understand the mechanics going on inside of that thing too. This one turned out to be a little longer than I wanted it to be, but we spent a lot of time on problem 153, and that's a really good problem to spend a bunch of time on. I hope you enjoy this. I hope you guys are having a great weekend, and I'm going to see you on Monday. You guys are doing such a great job, and I'm so proud of you, and I hope you keep it up. You're awesome.